Hey guys, how's it going? So today we're going to be going through MobileNet 1, 2, and 3. After that, we're going to actually be coding it from scratch so that we can actually have deep understanding of how these models work from a code perspective. Today I'm trying something new whereby I thought it would be a good idea for me to actually write everything down. This way I get to break these concepts into a more simple way. So one thing I like is that these MobileNet have what we call blocks. So essentially we can focus on each block as a single unit. So this way we get to break it down. And these blocks are reusable in different versions. So as we progress through explaining this concept, you will realize that as we go to mobile version 3, things get a little bit easier because we have covered them in version 1. So that's the good thing also. You have pretty much, if you have been following me on YouTube, you have realized that I'm a fan of like efficient deep learning. So I really like actually having efficient deep learning models, like because they can be deployed on resource constrained devices. So I'll keep on pushing these efficient deep learning content like knowledge distillation, neural architecture search, linear attention, all of these stuff, and they're quite mind-blowing because I feel like a lot of research have been poured towards training large models, right? So how do we then bring these models into like devices and stuff like that? So I think next week we'll cover also how we deploy large language models and how these inferences work and how these models are distributed towards different systems and stuff like that. So yeah, but without wasting any of your time, let's get into MobileNet 1, 2, and 3. So the first component that we're going to start to talk about is the Depthwise separable convolution. So I thought it would be a good idea for us to start with standard convolution so that we can actually understand why depthwise separable convolution was introduced in the first place. So a typical layer consists of convolution, then we have a base norm, then we have ReLU, like so. Then the input to this convolution, this block here, it consists of, it could be an image with height, like denoted as df, with width, df, and with channel. So this channel is going to be denoted as m. So we push this into the convolution, then we get the output. So the output is going to have df by n. So but these dimensions here are dependent on the convolution operations that we apply. Okay, for example, if we get df by df, so this means that our stride will be 1. So what is the stride of 1? Simple means that each kernel moves by 1 pixel. Okay, I'll try to visualize this in a second so that you get to understand. Then we have another concept called same convolution. That means we have padding. So essentially you can think of, I'm drawing here on the far right. So if like we have an image, so right, we paired this by adding pixel like so. So we can add pixels here, right? Then here, when we say stride of 1, so we have this thing called kernel. So essentially, we move on the image 1 pixel. So we move here, then the next, we move here. You see, next pixel, we move like so, right? Then n, essentially, it's the number of kernels, right? So so n here, it's going to be this dimension here. So it determines the dimension of the output. So it's the number of kernels. So for instance, so what's going to happen is that if we have an image like so we can have this kernel. We already draw this, it's 3 by 3. So it's 3 by 3, right? Then it's going to have the dimension of this image. So let's say there is it's RGB. So let's say here the channel is 3. So n, that n that I was talking about, it can determine how many of these kernels we can have. So maybe we have 10. So then the output it's gonna have x by x. So we can just, I'm putting x here just to say, okay, this is gonna be the height, width, but this end here is going to be here. So I'm trying to visualize this so that you understand how these dimensions work and what the output is going to have. Okay, yeah, that's that. So yeah, then we're gonna denote, please remember this, because as we continue, we're going to denote the kernel by dk by dk by m. So m, it's going to be denoting, it's going to have the same, yes, the same with the input. So we can see the input here has m, so it's called this channel. So also the kernel is going to have m. Okay, so just to show you again, I want you to understand this. So here I said 3 because I said it was coming from this channel. So you can think of this as m, 3 as m. Okay, then this 3 here is going to be dk, this 3 is going to be dk. Okay, I hope you kind of like have an idea of convolution. I know that if you've never heard of this convolution, these stuff might be that I'm explaining to you might sound like I'm explaining something out of this world, but I will try to explain as easy as possible, because I don't know the person who's watching this how familiar they are with these concepts. Okay, then the output is going to be represented as follows. So we can represent everything with this formula here. Like if we have an input, for us to get an output, we can represent it with this formula here. So n denoting this is the spatial dimension, so n, then this is the padding, right? Then we have the stride, then we subtract by the kernel, then we add +1. So if you punch all of these numbers, let's say you have an image, maybe here you have 10, you punch 10, here's a spatial dimension, you have your padding, you punch it here, you have a kernel, which is 3, you punch it here, you have a stride of 1, you're gonna get the output. So you will know what the output will be. Okay, so you can actually simplify everything within this formula like so. Okay, now let's estimate the cost. What will be the computation cost for us to actually do something like this? So what I have here on the left, on this part here, you can think of like this brownie thing here. It's an image. Okay, it's an image. Maybe this is what df by 6. You know, there's a 6. The 6 is like height and width. Then we added this green thing here. This green thing here, you can think of it as padding. Okay, so we pad with all the zeros. By padding, I mean we're just adding the pixel on top of the image. So let's say you have an image, we just add a pixel. I wish I included the real images so that you guys can actually have an idea, like an actual idea of how this looks like. But I hope you understand anyway. Then this yellow thing here that I drew, you can think of this as a kernel. So this is 3 by 3 kernel. Okay, so the reason I put it here is because a kernel is going to convolve the input image. That's the word that they use, convolved, yes, meaning that it moves across this, right? Or if the stride is 1, then it's going to move 1 pixel all the time. So it's going to start here, move here, move here, move here, move here, go to the next, move here, move here, move here, just like that. Okay, so we can denote this by 3 by 3 by m. Yes, you still remember I said m is the input. So if our input here we have an input like so, channel is going to be m, so it's going to be denoting that. So the cost of computation should be equal to the number of element in k by n by df by df. Okay, so what do I mean here is that you have a kernel, right? Yes, you have a kernel which is dk by dk by m. Okay, so then that kernel also have m, which is the number of channels there on there. So we have this thing here, right? Just like so. Are you still with me? So we have dk, we have m. Okay, then we say by n, yes, the number of kernels. Yes, the number of kernels. So we can have, like, explain this, we can have multiple kernels. So we denoted this as n. Okay, then we say by df by df. Yes, why? Because we're saying that this here has to move on this image. So what is the cost? What is this image? So it's df by df, so meaning that it has to move each pixel. So it's going to be by df. So we can simplify this by, okay, dk is going to be dk squared, then we have df squared by m by n. So this is pretty much the computation for us to kind of like convolve and go through this. Okay, so now you can see this computation. This is what motivated us to say, okay, can we come up with something efficient? And this is where they came up with depthwise separable convolution. We're trying to beat that that computation, but we still want to get the same accuracy. We don't want to lose that. Okay, so now I'll keep on repeating these concepts so that you get to understand them as we go on. Right? So we have an input image, df by m. So we know that this is, like, say, height, width, and channel. Okay, then we have a standard convolution. Then we have the output, like so. So I want you to know that these output are pretty much dependent on this on the operations that are happening within convolution, right? So n, it depends on the number of on the number of filters or kernels that we selected. Okay, so also the stride, the we see here we have the same. So padding stride is equals to 1, same equals to padding of 1. So that's why here we have df, meaning that we have the same dimension as the input. But this is not usually the case. I want you to know that it depends. We can say stride of 2, then we have to move pixel apart, and we're not going to have the same dimension as the input. These will be much lesser, to say to speak, if like the stride is 2. Okay. Then what we do, this is the concept of depthwise. Just stick with me now, right? So we said that, okay, in the standard convolution, we have dk by m, okay? We can break this thing into dk by 1, and we call this thing depthwise convolution. Okay, so this, you can think of this as like, it's going to convolve the special dimension, just dk by 1, right? Then for us to convolve this, yes, this dimension here, m, we use what we call pointwise. We create another we can say kernel 1, kernel 2, right? We use this 1 by 1. We call it pointwise convolution, right? Then we say by m, like so. This is going to be m. So it's going to convolve this. But the point here is that we have two components, which is the depthwise and we have the pointwise. Okay, so if you're still confused, let's try to visualize this. Let me just scroll here. So let's say you have an input, it have m channels, right? You have an m channel. So what you're gonna do is that you're gonna have your dimensions of the kernel. So it's dk by 1. Yes, like so. We explained this here, right? So it's gonna be dk by 1 by m, right? Because yes, each kernel is gonna go through each this component here, this component here, this component here. You can think of let me just use a YOLO thing here, all the way here, right? So essentially that's what this m means, is that for each kernel, dk by 1 by m, we're gonna go through this. The first one is going to come here, the second one is going to come here, it's going to come here. Okay, then we have the pointwise, which is 1 by 1 by m by n. So we put n here because we still want to get the same results as the standard convolution, right? So we still have m, but we have a number of kernels there denoted as n, so that we can get the number of the same number or the same output as a standard convolution. Okay, so now I think this looks a little bit clunky, so let me just scroll out so that you can understand. But now, what is the computation cost of us doing this, right? So because we have dk, so we know that this is going to be dk squared, so we're gonna denote it as dk squared. 1, it's a constant, so we're gonna say by m, so which is this m here, times df squared. Yes, because we remember that these kernels have to convolve the input, so we have this df squared also, because we can know that here is df, right? So this thing has to go through each pixel here, right? So df by df, so it's getting df. Okay, so this is the depthwise, this is this computation cost. But what about this one? So here we have we remove each constant, then we have m by n, which is this, the number of the channel that's always taking this from here. Then we have the number of kernels, n, like so. Then we have by df squared also. So this is going to be the pointwise. Okay, so now this is the formula like so. Okay, and then what did you say the formula for? This was the formula for the standard, right? So now let's put it side by side. It's going to be dk by dk by m by n by what is it, by df. See, it's supposed to be, you know what, let me simplify it, dk squared by df squared by m by n. So I'm just taking whatever is here, right? So I'm not creating something new, right? So so if we will work out this equation, if we will work out this equation and cancel some of these, we will realize that essentially this depthwise is much more efficient. So according to the, I think to the paper, it was taking 14.2% of the computation. So if we work out this and we say, for instance, I think this is going to cancel out with this, and this by this, then we left with n. Yes, you see we left with n, so which is 1 by n. So that's the cost right here. So you do the same with this. Maybe you do the same and say m, and you could realize that you left with dk squared. So if we take the configuration from the paper, MobileNet V1, which is 32 by n, the number of filters was 32 and dk was 3, the computation of the depthwise takes 14.2%, which is quite impressive. Okay, so that's why they're using depthwise separable convolution instead of the standard. So we can see how efficient it is, right? But the question that might come to your mind is like, is there any cost to this? Yes, it is. There is a cost because of the model complexity decreases. This is due to the number of weights. So there are certain weights that we loses. So if you do the maths, you realize that we're losing some of the weights with the depthwise convolutions. Therefore, the model complexity is going to decrease. So what the author did was to add 2 ReLUs to increase the complexity. So by 2 ReLUs, I mean if you have like maybe like conv, then you have batch norm, right? Then you're gonna have a ReLU, right? Then you have another conv, then you have a batch norm, then you have gonna have another ReLU. So why are they adding ReLU? Because ReLU add complexity. You know, it add that non-linearity. So essentially, it compensates for this loss of accuracy. so it does compensate, right? So yeah, it does help us to kind of like gain that small accuracy that we might have lost if we're just using this. Okay, so now let's take a look into the architecture of MobileNet V1. So what we start with is that we have the standard convolution, then we have the depthwise, pointwise layers, then we have the average pooling, then we have the pointwise convolution, then we have the full connected and softmax layer. So softmax layer is for the classification. So with this average pooling gets its input as denoted by 7 by 7 by 1024. So the average pooling it is 7 by 7 by 1. So because of this, which means that we're going to have an average pooling for this part, right? Then another part like so, another part like so. Okay, for or across all these this channel like so. So which means that the output of this average pooling is going to be 1 by 1 because it's going to be 7 by 7 like so. Then it's going to be we're going to get the output of 1024 by 1 by 1. Okay, then we push this towards the full connected layer. Okay, the author had number of 28 layers for their architecture. If we assume that the depthwise and pointwise are the layers themselves, okay, then we had a batch, norm, and ReLU across all the layers beside the fully connected layer. Okay, so another detail to the architecture was that they did not use max pool was not used, rather they used the stride of 2 to reduce the spatial dimensions. Yeah, that's what they used to reduce the spatial dimensions. So I think it could have been because the stride of 2 still keep information compared to max pool, which can discard some of the important information. Maybe that was the reason why they decided to use stride of 2. Okay, so now let's look into some of the good features that this model has, the architecture that we discussed. The author stated that the model wouldn't overfit, meaning that probability of overfitting was small. They had a less data augmentation. I think also I recently covered the mobile VIT, which is the hybrid architecture whereby we try to integrate CNN and VIT. So one of the point that the author said on mobile VIT was that essentially you require a lot of data augmentation for VIT models, but for CNN you do not require that lot of data augmentation, although data augmentation is still quite important, right? And this is because of these models have a built-in inductive bias for they can handle translation invariance. So we apply the same filter weight to the image, so we get to capture the edges and stuff like that. So even if like you turn around something, I think it can still be detected with CNN model. Anyway, then they say that we have less regularization, which is pretty cool, right? Yeah, then they did some optimization, and also check my other video whereby I cover efficient, what is it? Yeah, efficient net, right? So efficient net, it's quite good. It kind of like optimized the model across the dimension. So yeah, you can check it out. So I feel like these are the optimizations that they did to to MobileNet V1. So the first one was the chunking hyperparameter, so across the width multiplier. So they have an alpha here to reduce the number of kernel in the convolution. So instance, if we have let's say we have 112, here we have 64, we can reduce this by having some sort of like an alpha. So if like an alpha is going to be 0.5, then we end up with 32. The significance of reducing the channel, it is because we end up with the small model and we still keep the accuracy. So small model means that we get to have an efficient model when we're doing inference. So what they do is that this alpha thing ranges from 0 to 1. So 1 meaning that when alpha is 1, no shrinking is required. But if it is between 0 or 0.9, then we reduce the width of, right? So yeah, that was that. Then what they did was to introduce another component, which is to swing the model, which was called the resolution multiplier. So this reduced the input resolution. So yeah, like if we have an image, downsample the resolution, the resolution of the image. That's what I'm saying. Anyway, I'll try to leave the video of my efficient net. I think you will get to see how important it is for us to tune these dimensions, like with the depth and the resolution. And that's what efficient net is all about. It tries to find a systematic way to actually be able to compound scale these dimensions. So you'll learn a lot about them. But in this case, yeah, this is what they did to make sure that the model is quite small and we still get the same accuracy. So now we're gonna look into MobileNet V2. So I feel like the most important contribution from this paper was the inverted residual with linear bottleneck, which is what we're gonna actually try to talk about. But for now, before we get there, let's start with like the motivation. So we can think like if we're given an image and if we have a convolution operation, we get an output. This output here doesn't mean that all the important information is contained within this feature map. So there's just a few important information. And because of this, like you can think of like 3 channels are holding the most important information and the rest is just holding not so much information, not so much important information, right? So we want to actually select only 3 maybe channels or few channels, or in this case I think they use this higher dimension. So not to confuse you, I'll keep on using the word dimension as used in the paper instead of channels, but it's simple the same thing. So because of this, they needed to find a way in which they can be able to extract only the important information, because of this will actually help us to have less weight, so which means that the model will be fast. So like I said, the idea is that in real world, like if we're given an image, the information that is important make a small subset of all the possible tensors. So this is where the concept of manifold of interest comes into play. So we can think of this as a subset of feature map that are deemed to be important for final classification, just like I said, right? So to achieve a small number of channel, what we could use is the width multiplier. So we spoke about this, was that the width multiplier, essentially we introduce this alpha. So we multiply their dimension or channel, so we multiply it by the alpha. So this is essentially going to reduce the number of dimensions, right? That's one way we can actually go about it. So the problem with this, the problem with like naively reducing the dimension, one thing that the author realized is that essentially we face the problem of information loss. So the accuracy get to reduce, right? So let's take, for instance, let's say we have this feature map here, and we applied, so we have like 3 dimension, for instance, right? Let's say we discarded, let's say we had 128 and we discarded 125, just 1 3, right? Because of, after applying the convolution operations, we need to apply the ReLU. So what we'll really do is that it will lead to information loss, because it means that all the values that are less than 0 will be set to 0, right? And all the positive value will be the same. So essentially what I'm saying is that as information or the number of dimension decreases, then the loss increases, right? And the author played with this to see if like this was true. So what they did was that, okay, they tried with a situation whereby the dimensions was high, for his case here was 28, and they realized that actually the loss was low, meaning that the loss actually did decrease this time. So what was not increasing. So which means that these channels that we say that they're useless, they still carry some small information that helps the model to be accurate, right? So that's one explanation that we can interpret this, right? So but the point that I'm trying to raise is that we still need a way to still get the most important information, right? But we don't want to then apply a ReLU, because that is gonna then, our loss is gonna increase, because it's gonna be huge because of we have lost information. So we need a way to still keep information, like, so that we can apply ReLU if we want to. If we, some of you might say, yeah, but then let's discard ReLU, let's not apply ReLU. But that means your model is not going to be complex. It's just going to be a linear model. So it wouldn't capture like complex input, so to speak. So now the question is, how do we then exploit this important information, like these three channels that I spoke about, right? How do we then exploit them? We call this manifold of interest. How do we then squeeze that information, right? So we kind of like caught up into these two objectives, and we have these two problems that we need to solve. So this is where we're gonna introduce the inverted residual, right? So the observations is that ReLU causes information loss when applied to a lower dimensional activation. Right? So if our number of dimension, like I said, that I'll keep on using the word dimension, but you can think of dimension as this guy here. So if we have a low dimension, and this is like 3, like I made an example, then we're gonna have information loss. So which means that our loss is actually gonna increase. So that's a problem, right? So manifold of interest can be encoded on lower dimensional activation, right? So I'm gonna try to walk you through this visualization here, so that you can actually understand. So let's say that we have an input, right? Like we have height, width, and dimension, and what we do to try to actually be able to still extract the important information on lower dimension activation, we introduce this inverted residual with lower linear bottleneck. And how it works is that you can think of like we have an height, width, dimension, and we apply a pointwise convolution. Okay, so it's 1 by 1 by d by t, and we can think of this t as an expansion rate. So we try to expand the dimension. So initially we had, let's say this is our input, we had 3 as very low dimension, very low, right? But now when we multiply this dimension by t, essentially we try to expand this so that it can be huge, That's what this is going to do. We use this pointers. Remember that in the MobileNet V1 we spoke about the pointers. It's 1 by 1 by D. Then we introduce this T, which is the expansion rate or the expansion factor, right? Then we apply batch norm and we apply ReLU 6. I think we spoke about this now, that it's okay for us to apply ReLU because we expanded the channels. So this has been expanded, so we have a huge channel, right? So it's fine. It's just that we don't want to apply it where we have a very low dimension. Okay, after pointers we take this towards the depthwise convolution. The depthwise is like k by 1. So here we also apply the dt, so we have batch norm and ReLU. So remember that with this it's usually focused on the special dimension, the depthwise convolution, right? Then now we take this to the pointwise convolution. So the pointwise convolution essentially is going to compress the dimension. So it's going to bring this down here. Because of T here, it's a factor that can be tuned to decrease the dimension or increase the dimension. So it can play two ways. So here in this case we decrease the dimension. So hence here we don't apply ReLU because we have decreased the dimension. So we have taken them where they were. So we don't apply ReLU, we apply the batch normalization. Okay, so that's that. So another thing that the author do is that they apply residual connection to the final output. So let's say here we get the output, then we apply the residual skip connection. But this only applies when like stride equals to 1 because of we have the same dimension, and it's easy to apply to connect these two, the output and the input, when we have the same dimension. However, if we apply the stride of 2, because of the stride of 2 is going to reduce the dimension, then we don't do this, we don't apply this. So this is quite important because in code you'll see actually how we kind of like go about that, right? So yeah, but that's the most important thing. So the key takeaway to summarize everything is that we needed to get the most important information, the manifold of interest. We needed to get it, but we had a problem whereby we can't just get the important information, because to get that important information and we apply ReLU, then we're going to have information loss because of we extracting that from a very, very small dimension, lower dimension, so to speak, right? So what's the plan then? It's like, okay, how about we expand? We have this input which has a lower dimension, we expand it. Yes, we expand it like so. Here we just expanded it, then we apply ReLU. No, we apply ReLU, then we take it back, right? So we still achieve that goal of like saying that we want the output to be lower dimension. So essentially this thing that I just explained now, it achieves that goal, you know? So but if now you're about to visualize this in more like a blocks, you can think of it this way, like we have a small dimension here, then we expand this into using the pointwise, then we apply the depthwise, then we compress this back to the dimension the way it was, then we get this, right? So if we apply the stride of 1, then we can actually, it's fine, we can actually be able to connect these two. Okay, so like I said, they don't use expool, they use stride of 2 if they want to reduce the dimension. Okay, so and they call this inverted residuals, because I think in the previous paper what happened was they had something like this. These blocks were huge, right? So they were huge, but now it's more like opposite, it's reversed. So you see these small blocks are out, the big ones are inside, right? And then they call it linear. The reason they call it linear, it is because of that small guy, we don't apply ReLU there. So because of we don't apply ReLU, that non-linear functionality, it becomes a linear function. Hope it makes sense, right? So I feel like that's the key takeaways from the MobileNet Vision 2. As you can see, I didn't explain a lot of things because like the previous lot of blocks they were reused from the first MobileNet Vision 1. But this is the most important thing that was introduced. I hope this makes sense and you get a better perspective about this. So now we're going to look into MobileNet Vision 3. In the time of making this video, MobileNet V3 was the last vision from the series of MobileNet papers. So the first thing that the author did was to explore neural architecture technique. This actually enabled them to find the state of the art. So they explored automated search algorithm and network design that can work together to achieve state of the art model. The second block that they introduced was the squeeze and excite block. So you can think of this as an attention mechanism that point out channel we need to pay attention to. So essentially we can think of like we have a feature map, and from that feature map essentially we need to point out the channels which are important. So this way we get to improve the overall performance of the model. Okay, so to show you this squeeze and excite architecture, let's say here we have an input with height and width and channel. Then we push this towards a global pooling layer, which is 1x1 channel. So essentially here you can think of like we try to squeeze each channel to a numerical value. So we try to get a scalar value. So for each channel we have a scalar value. Okay, then we push these scalar values towards a fully connected layer, which is represented as a 1x1 by C divided by R. So you can think of this as a ratio for parameter reduction. So then we introduce a non-linearity, which is ReLU, which will also apply 1x1 by channel. Also here we have the ratio as a parameter for reduction. Okay, then we have a fully connected layer, which is the second one. Then we have a sigmoid. So we can think of this as like they give each channel some sort of like a smooth gating. So we want to weigh the channels, the importance of the channels, right? So that's why here we have sigmoid. So this is going to produce values ranging from 0 all the way to 1 meaning that that channel is very important. So yeah, that's what it is. Then we scale all of this and we add them to the input. We scale all of this, so we try to weigh all of the feature maps. So we try to see which one is important, then we add them all together, and that's it. Then coming now to the detail of the paper, what they did was to introduce hard sigmoid. So they replaced the sigmoid with hard sigmoid, mainly because of these sigmoid operations. They were quite expensive, so they introduced latencies. So this is how hard sigmoid was introduced, like so, right? From a visual perspective, we can see how hard sigmoid, this is like the orange line here, and comparing this to sigmoid, this is like sigmoid is this bluish curve. Okay, so this is like the difference between these. Anyway, then also switch has like this sigmoid operation in it, so this also can be expensive. So what they did was to introduce hard switch. So in the hard switch, you can think of like we try to use ReLU 6. So we have x plus 3 and the denominator of 6. So essentially hard switch improves the performance and it prevents the dead neuron, because if we can look at this plot here, it has this smooth curve here. So because of ReLU set everything to 0, so we can see that there's certain values that are not necessarily ignored. There's that smooth curve if we look into this here. So Another thing is that because of these switch activation functions, they are bounded, so they also can help in terms of like avoiding exploding gradients, so to speak. So yeah, you see, and that's all is it to it, right? So all them is like the same thing that we spoke about. We're gonna discuss them in the code, but this was like the main important concept that I feel like I needed to cover. But yeah, and that's all it is to mobile net V3. Obviously, they still use the previous blocks, so we're gonna code them up and we're gonna see how they work from the code. If you still don't understand it, I think it's okay because I'll still explain them in the code and I'll try to iterate more. I think if you don't understand, then that's my bad. It's not your mistake. Maybe I should try to improve into my explanation. But yeah, without wasting any time, guys, I really appreciate it. Now let's try to code these model up and see how far we can get. Okay, we're gonna start by importing the necessary functions that we're going to use. So it's gonna be touch.nn import as nn, then we're gonna say import mets. So just to remind ourselves, let's just look at the paper. So we're told that a nonlinearity call switch was introduced that when used as a drop-in replacement for ReLU. So this is because this switch function has an expensive operation, which is that sigmoid there. So they were trying to introduce a hide switch which replaces the sigmoid function with a piecewise linear hard analog. So this is how it's represented as. Okay. So if you were using switch, essentially we're gonna do X by then you can use a sigmoid function from PyTorch, then you throw the input inside there. So this is how you're gonna do it, but now we need to implement it this way. Okay, so what we're gonna do is that we're gonna just create a space here. So I'm gonna say class, then I'm gonna say h switch, then I'm gonna take from nn dot module as we imported there. So I'm gonna say def init, then we're gonna take in self dot in place equals to true. Then we're gonna say super h switch. Oops, made a mistake. Then we're gonna take in self. Then we're gonna say dot init. Then we're gonna say self dot ReLU equals to nn dot ReLU. I think I have to use small caps. ReLU 6. Yes, there is a function here. Then that's also gonna be in place. In place equals to true. Then we're gonna create a forward function, which is forward. Then we're gonna say self dot x. Then we return x by self dot ReLU, which we're gonna take x plus 3, right? We see x plus 3 divided by 6, like so. So that's how it is. Just for your information, you can always reuse these functions, so they are already given to you in PyTorch. So you can just do nn hard switch, it's gonna work fine. Or you can do, if you want to build a hard sigmoid, you can do it this way. So okay, so yeah, this is just like these functions that you can use. I'm just writing them like this so that you don't forget how they are implemented as we try to replicate them from the paper. Okay, then we have class, which we're gonna take h sigmoid. Then we're gonna have nn dot module, and we're gonna say def init. Then you take in the self. I'm gonna say in place equals to. Actually, I took this hard sigmoid from TensorFlow. It was written in TensorFlow. Then I had to convert it into Torch because it was not showing here in the paper, unless if I missed it. But so here it's non-linearity. So sigmoid, it's not here. It's a linear activation function, so it's not here. They just said that they're using they're gonna use it, but they did not show like the formula or something like that. So I used TensorFlow, unless if I missed it, it happens. But yeah, I didn't say it. Anyway, let's continue. So this is gonna be sigmoid, then we take in self, then we say dot init, then we gonna say self dot relu equals to nn dot relu relu 6, then we take in place equals to true. Then we're gonna do a forward pass, def forward function, then we take in self, then x, then we return self dot relu, which is x plus 3, then divisible by 6. Okay, these are the two main functions that we had. Before I actually forget, so we have to create this function called make divisible. So essentially, this function is going to make sure that it ensures that all the layers have a channel number that is divisible by 8. So yeah, it's quite very important that we have this function. So it's going to be make divisible. Okay, then we're going to take v. And before we continue, guys, I just want to say that if you're a fan of me just coding things up, let me know, or you just want me to walk you through the code. I just think like people prefer me coding things up because I get to explain as I'm coding, and you get to kind of like have a walkthrough with me. So I'm not sure what people prefer. So I'll like a feedback if yeah. Anyway, let's continue. So like I said, we try to ensure that all the layers of a channel number that is divisible by 6. So what we're gonna do is that we're gonna say if mean value, which is passed in there, if mean value is none, meaning that it's not passed in, then we're gonna take mean value is gonna be divisor. Then what we're gonna do is that we're gonna say new value is gonna be max of mean value, which is gonna be int. We're gonna say v, which is the given value plus the divisor. Then we divide this by 2. Then we have an integer division of divisor. Divisor. Then multiply this by divisor. Then so we need to make sure that round down does not go down by more than 10%. So we're gonna say if new v is less than 0.9 by v, then we're gonna say new v plus equals to divisor. Okay. Then we gonna return new value like so. Okay, yeah, that's that. Continuing. So before we continue, let's just look at because we wanna code up the squeeze and excite block. Oops, this one looks messy because we already wrote in a lot of things. So let me just paste this image here so that you can actually be able to understand, because I think let's do this. So before I code it up, I would like you to kind of like understand it, so it's more like a revision of what we already explained. So like I said, we're gonna have an input, then we apply global pooling of 1 by 1 by C, then we have fully connected layer, then we have ReLU, fully connected layer, then we have sigmoid. So like I said, this is more like an attention mechanism whereby we try to weight the channel. So we try to kind of like know which channels are important, or weigh them, that okay, these ones are important from a feature map, right? And we scale them here. Okay, so yeah, I hope that makes sense. Then yeah, let's try to code this one up. But this is like, I just wanted to show you this diagram so that you have a picture of what we're trying to code now. Okay, so we're gonna have a class which we're gonna call SE, which stands for squeeze and excite. We're gonna call it block. They call it block for the most part. Some people maybe they call it layer, but yeah, it's just the same thing. Then it's gonna be init. Then what we're gonna do is that we're gonna take in the self. Then we're gonna have the channel. Then we're gonna say reduction. So you still remember when I told you about that R, we had C divided by R. So actually let me write it as R instead of reduction. It's gonna be 4, so that you remember all the things that I said, right? So I try to be as close as possible. So we're gonna have a super, then we're gonna say block. We take in the self, then we say dot init, oops, like so. Then the first component was the self dot average pool, oops, average pool, which is going to be nn dot adaptive average pool 2D, which is going to be 2D, so then it's going to be 1. Then we're going to have the next step was the fully connected layer, so it's going to be self dot fc equals to nn dot sequential, which we can always reuse because we have two fully connected layer within this squeeze and excite block, so we can always reuse this. So it's going to be sequential. Then we have nn dot linear layer, which is going to take in the channel. Then we say make divisible, we use a function that we did. Then we're going to say the channel divisible by reduction. Then we're going to say 8 here, like so. Okay, this is going to be R. The next thing is going to be nn dot ReLU. Yeah, they did not say they're using ReLU 6, right? I mean, let's go to the paper. They just said ReLU. Actually, let's go to this diagram. Yeah, they just said ReLU here. So it's going to be ReLU. Then we're going to say in place equals to 2. Then we have nn dot linear layer. Then we say make the divisible yes, like so. Then taking the channel, then we have a ratio 8. Then we're gonna have in the channel like so. Okay, why is it complaining? Did I miss something here? Oh, maybe I did, but yeah, it's fine. We'll come back to it. Then we have a linear layer. Then after the linear layer, we have the softmax. So we're gonna say h dot sigmoid. Yeah, like so. Then we have all the components that we need. I'm going to say dot forward, taking the self input. Then what we do is that we say B, C, and we're gonna say X dot size like so. Then what we do is that we say Y equals to self dot we take the average pool. Yes, we take the average pool, taking X dot view B and C. So we try to squeeze the elements to the scalar, right? So Y equals to self dot fully connected layer. Then we say Y FC Y dot view B C, choose one by one. Then we return X by Y. Okay. Before we get any further, let's look into some of the blocks that we're gonna need to build. So some of these operators, as they're called here, they are actually reusable, so we don't have to build all the things. So for now, I think let's try to accomplish this conv block of 3 by 3 and another conv block of 1 by 1. So yeah, that's the goal. So we're gonna say dev conv, which is going to be 1 by 1. Then we're gonna say bn, which we're gonna take input and output. Oops, I made a mistake there. Input and output. Then we're gonna say return and then dot sequential. Oops. Sequential. Then we're gonna say dot nn dot conv 2d. Then we're gonna take in input, output. We're gonna say 1 1 0 because this is a pointwise convolution, so it's going to be bias equals to false. Then we're going to have nn dot batch, batch norm. So this is going to be 2D also, to take out, and we're going to have h dot switch. Okay, and that's all. We have to have now, it's going to be the oops, so that's gonna import it at the top. Actually, it's fine because we don't have to have it here since we're using the nn module. Then I'm gonna have def conv 3 by 3. Then we're gonna have also bn. We're taking the input, output, and stride. We return nn dot sequential. I forgot the spelling for sequential. Anyway, nn dot conv 2d. Then we're gonna take in the inputs, then we have the output, then we're gonna have array kernel size, then we're gonna have stride, then we're gonna have one bias equals to false. We have nn dot batch normalization to the output. Then we apply the switch, and yeah, I think that's all. And yeah, let's continue. Just gonna remove this import here. So now let's try to code in the inverted residual block. I don't know if you still remember, but we covered this in MobileNet V2. Just as a reminder, so it was this block right here. So I'm just gonna show you this image because we add the the squeeze and excite layer into this. So that's like the new change that we add into this layer. But yeah, that's what we're gonna try to build now. So it's gonna be class inverted residual. Then we're gonna take an nn dot module. Okay. Then we're gonna take in def, which is init. Oops, mistake. Okay. Then we're gonna say self input. We're gonna say hidden dimension. We're gonna say output. We're gonna say should be a comma output. Then we're gonna take in the kernel size. Okay, kernel size. We're gonna say use squeeze and excite. Then we're gonna say use. Then we're gonna take in inverted residual block. We're gonna say self dot init. Okay, so we're gonna make sure that we set stride is in, so making sure that our stride is whether 1 or 2. Then we're just gonna continue. Did we miss stride? Looks like it's complaining here. We didn't write stride in the input. Yes, so we have to write stride here. Okay, then we're gonna say self dot identity. It's gonna be equals to stride equals to 1, and input equals to output. So if this is true, then we know that we have to have the skip connection, right? So this is input, right? If this is true, then we know that we have to have the skip connection. But remember that we spoke about this when we were explaining this part. This blue thing here, we said that when stride equals to 1, we need to have the skip connection, right? Because the dimensions between the input and the output won't change. But when the stride equals to 2, then we will never have the skip connection, because stride of 2 is going to reduce the channel. Okay, so that's why we have that condition right there. Okay, so we're gonna ask ourselves if input equals to hidden dimension. If this is it, then what we do is that we say conv conv equals to nn dot sequential sequential, right? Then we're gonna build the depthwise convolution. That's what we're going to start with. Then we're going to have the nn.conv 2D. Then we take in the hidden dimension and hidden dimension. Then we have the kernel size. Then we have the stride. Then we have the kernel size -1, which is so we have an integer division of 2. Then you have groups equals to hidden dimension. Then we're gonna have bias equals to false. Then I'm gonna have a comma here. Then we're gonna say nn.batch norm 2D. That's right. We're applying this across the hidden dimension. Then we're gonna say apply the switch. If use hard switch, else we're gonna say nn.relu then we're gonna say in place equals to true. Okay, and now we implement the squeeze and excite as I showed you in that image, that the inverted residual in MobileNet has that squeeze and excite layer. So that's what we're gonna do now. So we're gonna say squeeze and excite layer. Didn't we build this? We did. So it's called EC block. Squeeze and block. We called it block. So yes. So we're gonna take hidden dimension. So we're gonna ask ourselves if use squeeze and excitation, else we're gonna say n.identity remain the same. Identity, yes, this should be nn. Okay. Then we're gonna have a pointwise layer, nn dot conv 2D. Then we're gonna take in the hidden dimension. Then we have output. Then we have 1 by 1. So there's a pointwise. Then we try to squeeze. We try to squeeze the channel. So no, we're compressing the channel. That's why. Hence, we will never apply the relu. So we're just gonna apply the two-dimensional batch norm. So we're gonna pass in output, and that's it. So here, we gonna have else. Okay. So I'm just gonna copy this, and we're gonna make small changes. So it's going to be self conv equals to sequential. Then we don't have, okay, we have to apply the pointwise. So can I copy this? Because we need a pointwise here. So was supposed to comment all of this. I feel like it might be confusing. Then I'm gonna copy this, because I'll just use relu, just copy it here. just copy this activation function. So this is the pointwise. Then we have depthwise followed by depthwise. Then after that we have the squeeze and excite block. So I'm just gonna remove this. So which is squeeze and excite block. Then we have we don't need this conv layer, so I'm just gonna copy it out. Then after the squeeze and excite, we apply the batch norm of 2D. Then after that, we close this with a pointwise layer. We're gonna apply nn.batch. So that's how it is. Yep. Okay. Then finally we do the forward pass, which is gonna be forward. Then we take self x. Then what we do is that we ask ourselves if self dot identity. So you still remember if we said that let me scroll up. We said that if this is true, we need to add the input with the self conv, right? The output. So it's going to be return x plus self dot conv, which is x. Else that means that the dimension are not the same. So we're gonna have return self dot conv x. Okay, and yeah, that's it. That's like the inverted residual block. So let's continue. Given the fact that we have all the components that we need, so what we're gonna do is that we're gonna try to construct MobileNet V3. So yeah, we're gonna try to build all of these blocks here. We have all of these blocks. It's just that now we're putting them together. That's what I'm saying. So because of that, I'm just gonna paste this code. So let's just walk through it. So what's going on here is that we firstly have these configurations. So these configurations essentially we can think of them as these expansion size, output, stuff like that. But so the K, let me just scroll down so that I show you what they mean. So the K in this case, we can think of this as the expansion factor for the layer. So it determines the number of output channel relative to the number of input channel. Then the T in this case is the depthwise expansion factor, so which determines the number of input channel for the depthwise convolution. Then the C is the number of output channel for that layer. Then the SE is a binary flag indicating whether to include a squeeze and excitation block in the layer. Okay, that's why here we have 0 and 1s. So the HS, it is a flag also for indicating whether we should use the hard switch activation function in the layer. Then the S essentially denotes the stride. Okay, that's what these configurations mean. Okay. Then here we just said if the model is large or small, then we have our 3x3 convolution. So it's this block here, right? Yes, it's the block. Then what we do is that we have these inverted residuals. Then we loop through all our configurations. Okay, and what we do is that we append this. So this block here is this inverted residual. So we append all of these configurations within this block. So you can imagine that we're creating multiple blocks, right? These are inverted residuals. So we're creating these multiple blocks here, creating all of these blocks. So shall I think? Let me just scroll down just to verify. Yeah. Then what we do is that we have solve.features, then we have an NN sequential whereby we take in on the layers, because we say layers dot append this, so we have the layers inside here. Then we build in the final layer, so we have the convolutional 1x1 batch norm. Yes, makes sense, because if we go to the paper, we have this 1x1 convolutional, pointwise convolution. Then we apply the average pooling. Yes, it makes sense, because we have this pool of 7x7. Then we have the output, and the final thing that we have is the classifier, whereby we have a linear hard switch and dropout, and also in a linear layer. So this is just the code for constructing the MobileNet V3. That's why I didn't have to code it, because we just like having these components come together. And these are the configurations, like so. So yeah, I think that's all that is to it. Yeah, I think I'll leave the code for you guys to kind of like if you want to go into much depth, but that's all it is to this. I really appreciate it if you have watched to this point. Yeah, I'll see you in the next one. Thanks, bye.